All right, so we did the first two in chapter exercises. Now we are going towards the third one. First, let's read this theory. So you have the first principles of differentiation. Yeah, we don't want that. We already know it. Yeah, whatever. Just move on. Derivative of inverse trigonometric functions. Okay, this is something I want to see. So if y equal to sin inverse of x, where x is between -1 and 1, uh, and y is between negative pi upon 2 to pi upon 2, then, okay, I mean, that's obvious. Like this is, this part is obvious. Okay, uh, fine. So, which is finite and non-zero for y. Wait, oh, so yeah, like this thing, cosine y is equal to square root of 1 minus sine squared of y. This is, yeah, okay, this is kind of weird because this thing's like cosine y, is this necessarily positive? Well, we did say that y is in negative pi upon 2. So maybe you can say it. Okay, interesting. So what you're saying is the derivative of sine inverse of x will always be 1 upon square root of minus x squared. Interesting. And similarly, you can do something for cosine inverse of x. Oh, so like that's why you define the sine inverse of x for this range, and then cosine inverse similarly for the 0 to pi range, because in that range your sine is actually positive, right? Yeah, it's starting to make sense now. Okay, this is, wow. I didn't think of it like that, but yeah. So what that means is the derivative of sine inverse of x being square root of 1 minus, it will just be like 1 upon square root of 1 minus x squared all the time, right? Doesn't matter what x is positive, negative, what's happening. We don't care about it. It will always be like this. Oh, so in the last time when we had the derivative of cosine inverse of 2x upon 1 plus x squared, I could have just took the derivative using this formula and not have worried, because the way it's defined is that it like ensures it will be fitting into the formula all the time. Yeah, I think that does make sense, huh? So then for cosine inverse x as well, you can always use this formula without worrying, because, right. Okay, what next? Y to the inverse of x. So once again, x equal to tan of y, which means that dx upon dy equals to square of y, which is just 1 plus tan square of x, which is always finite and non-zero, well, whatever, which is just 1 plus x squared. So that means dy upon dx is equal to 1 upon 1 plus x squared, right? And okay, that is actually, that is in fact easy. It's doable, not a big deal, right? Yeah, so dy upon dx, it's 1 upon 1 plus x squared. Doesn't matter what x is. It's negative, positive, whatever. Or y equal to cot inverse of x. Yeah, you can do the similar stuff. So because the domains are, because the range things are in a way that, um, yeah, right. So because the range of these functions, sine inverse and cosine inverse, were such that the other part, so it would be positive, right? For example, this part sine y, cosine y, right? That comes in the derivation, like that would be positive, right? So that's the way these are defined, huh? Well, yeah, that's actually interesting. Nice. You know what that means? I could have just differentiated the function that I got the last time without having to worry about its sign or whatever it is or what the function actually is. Yeah, I should have done that. But whatever. Just move on. Differential coefficients of inverse trigonometric functions. Okay. When by the way, the differential coefficient, that just means a derivative, nothing else. Nice. Logarithmic differentiation. Oh yeah, I mean, I use this a lot when you have a bunch of functions multiplied, then just use this method. I mean, actually, I already know what the result will be. Like, if we got this thing f1, f2, f3, a bunch of these functions multiplied together, and you want to take the derivative of these guys, what you do is you just take the derivative of the first guy, so like f dash 1, and then repeat all of these functions. Then plus you take the derivative of the second guy, repeat, and yeah, just keep on doing this. And there you go, you got the derivative. And you can also like prove that this is the thing by using this method, right? I won't do that because everybody knows it already. Okay, that's awesome. Okay. Regarding y is a function of x in collective terms, it's an implicit function. What? Oh, okay, fine. So you mean differentiate both sides without having to worry about finding, a function form. Yeah, don't do that. Just differentiate. Right. Sure, you can do that. We have been doing that for ages now for differential equations and whatnot. Differentiation using substitution, I know that. All right, let's start. Okay, I get it. Look, I know this. Derivatives of higher order. Oh yeah, these things. So we'll prove them on the spot, so we don't need to read them right now. Oh, this is something that you should know. Differentiation of determinants. So say you want to take the difference of a determinant, right? How do you do that, right? So what I'm talking about is you have this determinant, um, f of x plus delta x, and then g of x plus delta x, and h of x plus delta x and whatnot, right? So you have a derivative like this, and then you want to subtract from them f of x, g of x, h of x, and so on. How do you do this thing? Uh, yeah, this is something like, how do you take this difference? Yeah, uh, can you just do the difference thing like without how do I explain what's going on? What you can do is you can actually write f of x plus delta x is like f of x plus delta f. Does that make sense? You can do that thing, and once you do that, you will be able to expand this thing using the properties of the determinant, right? And after you have expanded that, just take like, yeah, just take the actual difference, and then you'll have the thing. Does that make sense? Let's do it on a 2 by 2 derivative first, and then you will understand what I'm talking about. So the way this works is like you're taking the derivative of each row, right? Why is that? Why are you doing that basically? It's kind of hard to explain without actually, I mean, telling you about vectors and all that stuff, but come on, okay, let's just do it. Who cares? So this is very weird, but just, yeah, just think about what I'm doing. Okay, if you want to prove it, you can prove it by yourself. But what I'm going to do is not give you proof, but give you kind of like an idea about what's going on. So this determinant, we can think of this like this thing. So each row vector will actually think of the row vector as a vector now. So the first row will call it like, I don't know, u vector. So u vector is a function of x, which is some variable, I don't know. Then you got, let's just say v vector and then w vector. So this box product, which is a scalar triple product, this represents the determinant. Now you want to take the difference uh, of this thing, right? So like, this is hard to explain, isn't it? Yeah, it is hard to explain. Okay, first of all, I'm just going to show you what I mean by the difference. So after some progress in x, what happened is that this now became this thing, u plus delta u, then v plus delta v, and w plus delta w. These are the new row vectors, all right? Now, because all the operations like the cross product and the dot product in this thing are distributive, what you can do is like define a new multiplication symbol. It looks weird, but trust me, I know what I'm doing. So define a new multiplication symbol. I'm gonna call it like star, and write the determinant like this thing, u vector plus delta u vector, or whatever this is. Actually, just write this determinant first of all like that. Just just want to explain what's going on. So it's a u vector star v vector star w vector. So what are the properties of this star thing? It is distributive and it is associative, but it is not commutative, right? So that's the properties of this star. Now, using that, you can write this thing. So basically, it just becomes kind of like multiplication. Okay, yeah, like distributing on the multiplications. Does that make sense? Like how you do it with polynomials. You got x plus 1, x plus 2, x plus 3, something like that. You distribute the thing, right? So now you're going to do that. Although this star, we don't know what it actually means, what it does. But what we know is that you can write this determinant like this, and then this star is associative and everything. Right. So over here, this star, this would be the cross product symbol, and over here, the star would just mean a dot product. Does that make sense? But then I'm just going to write it like this. I only want to think about the properties of this star and not really what it actually is. So as long as you can agree that um, this thing is distributive and it's associative, right? And as long as you can agree on that, you can use this that I'm doing right now. Okay. So first of all, you got u plus delta u, then you want to do star, and I will just multiply now. So like v vector star w vector plus delta v vector star, let's say delta w vector. Then you got v vector star delta w vector and w vector star delta v vector, right? Cool. And then you're going to do this thing times all of that, right? Yeah, like u vector star v vector star w vector, right? Plus u vector star. So you got two deltas over there. So delta v vector and then delta w vector. Why am I writing these two delta things inside? You will see what's going on. Then, okay, this is something that we care about. So u vector star v vector star delta w vector. Okay, then this is also something we care about. Oh, this should have been the opposite. I mean, I already told you it's not supposed to be commutative. So this is supposed to be like this, not the opposite thing. Okay, so it's just u vector dot delta v vector dot w vector. I'm saying dot, it should be star, whatever. Okay, then do the same thing with delta u vector, right? So you will have like delta u vector, delta v vector, delta w vector, and all that stuff. So delta u vector times other stuff that contains deltas, right? And then you will also have this thing, the delta u vector star v vector star w vector. Now, what I'm going to do is that anything that contains more than one delta is negligible. So this is negligible. All of this is in fact negligible because this contains like delta and this already has one delta. So yeah. So these are the four terms that we care about. Now this thing minus of u vector star v vector star w vector, that's going to give us actually the change, right? So this thing, I'm saying this is negligible, but that's only under the limit, right? So when you're doing the derivative correctly, how do I explain this thing? But yeah, that's what I'm saying. So once that's done, You have subtracted the original value from the new value. Now divide by the change in x, right? And there you go, you got your derivative. It should be dx and dw vector, but you get the thing, right? You get that it's going to be a limit and everything. So now you can write it like this. The box of u vector, v vector, delta w vector, and then all of that upon delta x. But then you can actually pull that inside because it's a determinant, by the way, right? Because it's a determinant, you can do that. If it was a like matrix or something, you would not be able to do this thing. It's just this thing, delta w vector upon delta x. And then, yeah, just sum this up. So like two more terms like this. So the next term will be like u vector delta v vector upon delta x, and then w vector. And yes, there are like these terms as well, but then we already neglected them. And now just take the limit. So this will just be this thing, dw vector upon dx, and then dv vector upon dx. Then you got this stuff. It should be this thing actually, du vector upon dx, and then v vector w vector, right? Now, isn't that exactly what they are doing? They are taking the derivative of this row first. That's what I'm doing in this determinant. Then they are taking the derivative of this other row, right? So that's what I'm doing in this determinant. Yeah, and then finally they're taking the derivative of the third row. So that's this thing. There we go. We proved that this formula works. And of course, you can do it for higher order determinants as well. Okay, that's awesome. And L'Hospital's rule. Yeah, we know that. Uh, I mean, we should prove this and everything, but then I don't want to. Ancient princess 3. Right, let's do it. You don't need all of this. First question. Derivative of the function 1 plus 3x squared times 2x cubed minus 1 with respect to x is. Okay, well, that's actually. Why are they doing something like this? What is this? Isn't this supposed to be continuity and differentiability? Why are we doing this all of a sudden? I don't know. Anyway, they want what? The derivative of this function. So first the derivative of that guy, which is just 6x times 2x cubed minus 1, and then what is this? 6x squared. Take a 6x out, which is 2x cubed minus 1, plus what is this? 1 plus 3x squared, right? Like plus x plus 3x cubed. It looks good. So 6x times 5x cubed plus x minus 1, which is B. Next question. Second. Second is derivative of the function, this function with respect to x is x minus 1 upon x minus 2 upon x minus 3. Yeah, whatever. So just take the natural log and do the thing, right? Yeah. Wait, what happened? Oh no. Okay, that's not good. Ah, fine. Just keep on going. So derivative of this function with respect to x is just take the derivative. Okay, so just take the natural log and then differentiate. So just have this thing 1 upon x minus 1 minus 1 upon x minus 2 minus 1 upon x minus 3, and then multiply this thing by the original function because you have to do that, right? Like y dash upon y is equal to this that we just did. Now y times of this thing. So yeah, you will have it's actually hard to explain what's going on, right? So it's supposed to be x minus 2 x minus 3 squared, huh? Fine. So just 1 upon x minus 2 times x minus 3 minus x minus 1 upon x minus 2 times x minus 3, right? Squared, of course. And then minus x minus 1 upon x minus 3 squared times x minus 2 squared, right? So it's this thing, x minus 3 squared, x minus 2 squared. First, we just have this like x squared minus 5x plus 6, okay? and minus, so you will have x minus 1 times x minus what? 2, and then x minus 3 as well. So basically like 2x minus 5 times x minus 1, right? X minus 1 times 2x minus 5, sure. So this is just x squared minus 5x plus 6 minus 2x squared. You got minus 2x and minus 5 is minus 7x. So plus 7x and then minus 5. Yes. And then all of that upon this thing. Yeah. H is going to be what? It's supposed to be squared. Minus x squared plus 2x plus 1 upon x minus 3 squared, and then you got x minus 2 squared, which is this, right? D. Next question. Let's go to third. Derivative of the function square root of 1 plus x squared, which x is, so just 1 upon 2 square root of 1 plus x squared times 2x, which is x upon square root of 1 plus x squared, which is a, I think. Next, fourth. Derivative of the function. Why am I doing this? This is not continuity or differentiability. It's just normal differentiation. Fine. Derivative of this function is, so the original function times what we have after taking natural log. So this will just be, take that 1 upon 2 out. It's just 1 upon 1 plus x, and then you got, it's like minus plus, right? So plus 1 upon 1 minus x. Doing it, you just get like 2 upon 1 minus x squared, right? So this will just be this thing, minus x squared, and then you will have this gone. So yeah, square root of, one of them cancels. Oh yeah, so just 1 upon 1 minus x, and then you have square root of 1 minus x squared, right? Sure, which is, I think, B. Next question. Let's go for fifth. Fifth is the derivative of the function cosine cube of x and then sine of x with respect to x is this thing, then a is, okay, so it's just 1 minus sine squared of x, which is basically like cosine squared. So cosine squared times 1 minus a sine squared, right? We are saying that's the derivative. Okay, interesting. It's like cosine square minus a sine square cosine square would be, well, just take a derivative of this thing and we'll see what happens. So this is like 3 cosine squared sine x. Yeah, and then also derivative of cosine, which is negative sine, so just negative, and then you got sine squared over there. Oops, squared. Looks good. Then the derivative of this guy, which is like cosine cube times cosine once again, so just cosine power 4. It's like cosine square, and then you got cosine square minus 3 sine square, right? Which is cosine square times 1 minus 4 sine square. So a is just 4. Yeah, a is 4, which is option number A. Next question. Derivative of the function x e power x sine x with respect to x at x equal to 0 is, just like I told you, derivative of the first function, then derivative of the next function x e power x sine x, then derivative of the last function x e power x cosine x. So e power x times, oh, and you want at x equal to 0, this will be gone. This will be gone as well. It's just, this will be gone as well. Wait a second. Oh, it will be 0 in fact. So C is the answer. Huh. I should have known. Seventh. Seventh is the derivative of the function with respect to x is of this function. Okay. Oh, first of all, you could actually simplify this. So multiply by 1 minus cosine x on top and bottom, we just get 1 minus c upon s, right? Which is like, I guess you could simplify it right away. You know what? No, let's skip all that and just do it the proper way. So this will be 2 sine of x upon 2 cosine of x upon 2 upon, this thing is just 2 cosine square of x upon 2. So this cancels, it's just tan of x upon 2, right? Derivative of this guy will just be 1 upon 2 secant square of x upon 2, right? So that is going to be b. 1 upon 2 because of chain rule. 8th, derivative of the function, this function with respect to x at x equal to what 3 pi upon 4 is. Fine. So sine x minus cosine x. Mm. Hey, I know one way of doing it. It's like natural log of square root of 2 times. So there's 1 upon square root and everything. So you can write like sine of x minus pi upon 4, right? Yeah, that looks good. So this will just be 1 upon 2 natural log of 2 or natural square root of 2 plus natural log of sine of x minus pi upon 4. So the square root of 2 thing doesn't actually matter. So you can just do this thing, this plus c, where c contains that constant, right? Like natural log of square root of 2. Now the derivative of this thing, that will be just something upon sine of x minus pi upon 4 and like cosine of x minus pi upon 4, which is just cot of x minus pi upon 4. Yeah, that's the thing. So, oh, and you want this at x equal to pi, what, 3 pi upon 4? That will be cot of pi upon 2, I think. Wait, what? Oh, that's not defined. Huh. No, okay, cot, not tan. Sorry. That's 0, right? So at pi upon 2, I think. Yeah. So it's at pi upon 2, it's going to be 0. Next question. 8th is done. 9th. 9th is the derivative of the function uh, tan inverse of 1 plus x upon 1 plus x with respect to x is. Why does it look like I've seen that somewhere? What about just say x equal to tan theta, then this is like tan of pi upon 4 plus theta, right? So yeah, just pi upon 4 plus tan inverse of x. I guess you can do that, right? I mean, like tan of pi upon 4 plus theta. Theta is just something that is in the first quadrant. Wait, no. Okay, theta is something that's in a negative pi upon 2 or something. Uh, Not actually the range we are looking for. And this plus pi upon 4 should give everything, right? Huh. I don't know. I don't know. I get what's going on, but then it's very weird actually. It's like anything actually. When you said it's pi upon 4 plus theta, why do I even care about it? Just differentiate it because, yeah, like the result is the same, right? So it doesn't matter what route you took and whether or not that route was the correct thing all the time, as long as you get the same result. Because, yeah, it's just like a shortcut. You could do it the proper way or you could do it the way I'm doing. Both will give you the same result. Of course, this is the not so good kind of way, and this is the best way to do it. But still, I'm going to use this one because it's faster. So this is just what, 1 upon 1 plus x squared? Yeah, 1 upon 1 plus x squared. So it's supposed to be d. Next question. 10th. 10th is the derivative of the function y equal to 1 plus 1 upon x to the power of x with respect to x is. Alright. So, oh, okay, I see what's going on. Except it's not a limit, so you can just do e and fine. Okay, so the rate of this function, yeah, fine. You can write this as like e power x natural log of 1 plus 1 upon x, right? And take the rate of this guy. So it will just be this exponential, and then you have the derivative of this inside stuff. So the derivative of x natural log of 1 plus 1 upon x. But then remember that this thing is actually just what we originally had. So then it's just this thing. So what is this going to be? This will be natural log of 1 plus 1 upon x plus x upon 1 plus 1 upon x, and that times of negative 1 upon x squared, because you need that chain rule. Yeah. Now that will just be, let's see, negative 1. That x is still this, like x plus 1. That should be doing it. So negative 1 upon x plus 1, right? So it's natural log of 1 plus 1 upon x and then negative 1 upon x plus 1. Yeah. Oh, okay. This is kind of not what should have been happening. So what you're saying is, okay, y dash is just equal to y, because this was what it initially was, right? That times natural log of 1 plus 1 upon x minus 1 upon x plus 1. Interesting. Okay, I think I know what to do. Like 1 upon x times x, and then that goes on the top. So it's natural log of y. Y, natural log of y upon x minus 1 upon x plus 1. Why is that? Why is that like? It should be negative, right? Why is that not negative? I mean, it should be negative. Sure. Why is there positive everywhere? And where's the natural log? Just what happened? Huh? It's not y upon it's natural log of y upon x. What is wrong? It's just a rate of this thing, yes, and just like natural log of x upon x. I mean, seriously, what's going wrong? There should be this natural log that's not here. So what do we say? We just say none of these. Yeah. Yeah, right. It's D. Next question. 11th. 11th is the rate of the function natural log of x to the power of x plus what's this x power sine x with x at x will do 1 is n. Okay, let's just tell you the things. F power g, the rate of this thing is just f power g times uh wait a second times this thing g f dash upon f, because like natural log of f, the rate of that thing, just this. All right. Yeah, and they just got g dash times natural log of f. Yeah, this is the derivative of this guy. So for this function, where did that go? Natural log of x to the power of x. This will be what? Uh, Once again, the same thing, natural log of x power x. And then you have, so gf dash upon f, which is just x, and then you got the rate of this thing, just 1 upon x upon natural log of x, like 1 upon x natural log of x. Yes, that is this thing, right? So just 1 upon natural log of x. Plus g dash is perfect, which is so g dash is just 1, so natural log of it, which is like natural log of x. Yes, right. And wait, and what do you want? You want at x equal to 1. Well, that is not good, because natural log of 0, we are not going to be able to do that. Oof. Is that seriously what I'm thinking it is? It's supposed to be at x equal to 1. This will be natural log of 0. It's not defined. Yeah, that's the answer. D. Don't even need to do this the other part because it's already not defined. 12th is if y equal to cosine of x plus y, then dy upon dx is negative sine of this is a differential equation. Sorry. Okay, sorry. Dy upon dx, right? So y dash is equal to negative sine of x plus y times, well, that inside stuff, which is 1 plus y dash, right? Yeah, which means y dash is equal to negative sine of x plus y upon 1 plus sine of x plus y, I guess. Yeah, C is the answer. Next question, 13th. 13th is if x power 2/3 plus y power 2/3 equal to a power 2/3, then dy upon dx is, okay, so like 2/3, and then you got x power negative 1/3 plus 2/3 y power negative 1/3 is equal to 0 or whatever. This cancels. Oh, and should also have actually y dash over there. Y dash is equal to 0. That just means like y dash is equal to negative x power negative 1/3 upon y power negative 1/3, which is like negative y power 1/3 upon x power 1/3, just like y upon x power 1/3, right? Yeah. So that is A. Next question. 13th is done. 14th. 14th is if x power y equal to e power x minus y, and another differential equation. Okay, I mean, you want to form a differential equation. That's what we're trying to do, of course. And dy upon dx is this thing. then f of x is equal to okay, let's just do it. So wow, I mean, seriously, what is this? First of all, just take the natural log on both sides. You will just get this thing, y natural log of x is equal to x minus y. And now differentiate. So y upon x plus y dash natural log of x. That's equal to 1 minus y dash. Yeah, so like y dash. That's what you want to find, right? Yes, so it's just 1 minus y upon x upon 1 plus natural log of x. Yeah, looks good. So, and that's what? Oh, okay. You have to write this like 1 plus fx squared and then fx upon this. Okay, it's very weird. Just x minus y upon x times of 1 plus natural log of x, right? Where have I seen natural log of x? It's just this thing. Like y natural log of x would be this thing. So, seriously, what is this? Huh. Oh, okay, okay, fine. So, like y is equal to x upon 1 plus ln x. This is what you should substitute in there and then get the thing done, right? So just do that, and so like fine, this cancels. 1 minus 1 upon 1 plus ln x upon 1 plus ln x, right? So this is ln x upon 1 plus ln x squared, right? So f of x is just ln x, which is b. Next question, right? I mean, of course, this is like a function of x. There's no y involved in there, right? So you have to substitute y as a function of x, right? If x power t times y power q equal to x plus y power t plus q. Wow, good thing that's an equation. Like it gives y as a function of x and not an identity. Then I would just vomit. Okay, then d squared y upon dx squared is okay. Oof, doesn't look good at all. Take the natural log first of all, which is got p natural log of x plus q natural log of y is equal to p plus q times natural log of x plus y. And now differentiate. So what you will get is p upon x plus y dash, also like q y dash upon y actually. That will be p plus q and 1x plus y, and then you got 1 plus y dash. Sure. And what do you want? You want like y double dash. As if it's already not bad enough. So just multiply by x plus y, I guess. Then this will be like p plus py upon x plus qy dash plus qxy dash upon y is equal to p plus q times 1 plus y dash. Wow. Trying to simplify some stuff. So qy dash, that cancels. Okay, this cancels. It doesn't really matter. It's just constant. So you have py upon x plus qxy dash upon y is equal to py dash and plus q. Huh. Let's multiply by xy or something. And how bad would it be? It's just py squared. Okay, it can be really bad. I don't like this. Okay, q x squared y dash is equal to p x y dash plus qxy. Okay. Yeah, well, that's a little. This is just awful. Fine. So that combines, and then you just have. Okay, you know what? No, let's not do that, because what you want to do is isolate y or something. Yeah, that should be the goal. But okay, that's actually really hard to do. You can't do it. So just differentiate. Just differentiate like that. Okay. Then you have p y dash upon x and then minus y upon x squared. Okay, plus q. What is this? Seriously, this is just so bad. Okay, first of all, you just have this thing y dash upon x minus y upon x square, and that times y dash, and then you can have the other guys letters like this qx upon y double dash, that's equal to py double dash, right? So our y double dash times p minus qx upon y, that is equal to this thing, y dash upon x minus y upon x square, and all of that times p plus q y dash. Sure. Wow, it's getting horrible. And now what? I mean, how did I get this thing out of? No, that's just not looking good. How can you get something like this? How does that make sense? No, this doesn't make sense. Like, okay, you could just substitute what y dash is, right? You already got y dash. Now, because there's no y dash involved over there, so just substitute that inside and then sure, that's one way of thinking about it. Can't we just figure out what y is as a function of? No, you can't. That's not doable, unfortunately. Oof. How long is this? Seriously. Fine. And now you will have to put in what y dash. Nah, this is just too much, right? This is just too much. There must be some other way to do this. This was y power p plus q. Well, I'm thinking of something like this. X upon x plus y power of p, and then you got y upon x plus y to the power of q, that is equal to 1. Not helping. Still not helping. Yeah, this won't help. Oh god. No. Just no. You can't find y as a function of x. Then this is, and neither can you just isolate it. Just horrible. Okay, we'll have to put in what y dash is. There's no escaping it. Fine. Then let's take the y dash out of there. So just y dash times q x upon y minus p is equal to q minus py upon x, right? Yeah. So this just becomes y dash upon y times qx minus py is equal to qx minus py upon. Hey, I could have done that earlier. Why did I not do it? Why did I not do that? I could have already done that, right? Oh god. Seriously, I should have done that. So it's qx minus py and that upon what? X. This cancels. What do you get? Just get like y dash is equal to y upon. I should have done that instead of all of this. So there you go. That's the thing. Y dash is equal to y upon x. Huh? Well, that's interesting. Maybe there was some better way of doing it. I don't know. Well, anyway. So what would happen if, say, you put y is equal to k times of x in this thing? Then you would have like x power p plus q and then k power q is equal to x power p plus q and 1 plus k power p plus q, right? Or so it seems. Yeah, wait. That should be the thing, right? Huh. Weird. So if I did put y equal to kx, this would happen. Okay. And this will cancel out. So that just means k is a constant because, and that's why this is happening. Oh, I should have known. Okay, this was actually very homogeneous in the first place. So I should have already just put y equal to kx in this and then got the thing. Right, I should have done that. I get it. Well, whatever. Now we have it, right? So y double dash is just 0. Yeah, because, right, like y is equal to y upon x. Okay, do I really have to show this to you? Differentiate it once again. What do you get? Um, you will just get like y double dash is equal to y dash upon x minus y upon x square. And then what's y dash? It's just y upon x. This will just be y upon x square minus y upon x square, which is just 0. There you go. That's the y dash thing. So it's D. Huh, interesting. Which means that next time I'll see something like this, I'll just put y equal to kx. Okay, next. If x is equal to a times 1 minus t square upon 1 plus t square and y equal to this thing, then dy upon dx is, just do it like this. X is equal to a cosine theta, y is equal to b sine theta, then what's dy upon dx, right? But of course, cosine theta equal to 1 minus t square upon 1 plus t square. But like t is just tan of theta upon 2. If that is, you know what, just put 2 theta. Because, yeah. So now tan theta is t. Then dy upon dx, that's just going to be, what? It's like 2 and all that stuff. Just b, so negative b upon a cot 2 theta, right? Yeah. Which is negative p upon a, and then in the denominator we got 2t, and then you got 1 minus t square, I guess. Yeah, that's what dy upon dx is. So where will we find that? Okay, it's t square minus 1 in that case. T square minus 1 b upon 2at, which is d. Next question. That's 16th d. 17th. 17th is if x is equal to ax is equal to a times what? X is equal to ax. Seriously, what is this? That just means a equal to 1, right? Yeah. I think this ax was not supposed to be here. Or was it? Let's do it this way. X is equal to a cosine t plus t sine t. So just write like c, c plus t sine t. Okay, and y is equal to a times sine t minus t cosine t. It doesn't matter. Yeah, like it doesn't actually matter whether it's a or not, because either a is 1 or even if it's there, it's the same in both of these expressions. So dy upon dx, yeah, just do it. uh Cosine, it's not supposed to be there, minus cosine once again. Okay, then you got plus sine times t, okay, upon minus sine, then plus sine, and then you got t times cosine. So it's just tan, right? Tan of t. That's dy upon dt. So it's B. Next question. Like, looks like that. Okay, next. 18th. 18 is if y equal to sine inverse of x square upon x power square of x power 4 plus a power 4. Then dy upon dx is, okay, I have seen that somewhere. It's this thing, right? X square square root of x power 4 plus a power 4, it should be just a square. Tan inverse of x square upon a square, because like positive numbers and everything. So it's in the first quadrant, then y is just this. Sure. So dy upon dx is what? This thing. 1 upon x power 4 plus a power 4, and then this guy just 2 upon a square times x, right? Yeah. So e power 4 plus x power 4, that goes to the top, 2a square times x. That should be the thing. Which is this thing. Okay, so k is just 2. Next question. So 18th is done. 19th. 19 is if y equal to natural log of x upon x, then find d square y upon dx square in terms of x. Oh, yeah, it's doable. It's just 1 upon x square, and then you got negative natural log of x upon x. Yeah, that was, maybe that was too easy. Yeah, this should not have been that easy, right? Sure, it's like 1 upon x, and then that's just 1 upon x squared, and then there's, yeah, I just 1 minus natural log of x upon x squared. Uh, oh, that's y dash, sorry. Okay, for a second I thought that was just too easy. It's not. Okay, so that's y dash. Let's do y double dash now. Rid of this guy, just negative 1 upon x cube, then negative 2 upon x cube. Yeah, right. Times 1 minus natural log of x. Right. Just x cube. But negative is not supposed to be there. Like negative 1, negative 2 plus 2 natural log of x. So 2 natural log of x minus 3 upon x cube, which is C. Next question. 20. 20 is if y equal to x plus tan of x satisfies the differentiation equation. It's differential equation, same stuff. Cosine square x d square y, fine, c square y double dash is equal to, so x of course, is equal to k times of y minus x. Okay, then k is, oh, sorry, what am I doing? This is not a differential equation. Okay, I mean, okay, this is the differential equation. The original thing is this, so this satisfies this thing, right? Just put that in there, of course. So y equal to x plus 10x, just put that in. What's y dash going to be, first of all? Just 1 plus secant square of x, which is, okay, it's not very satisfactory. Fine. What's y double dash going to be? So 1 plus 2 secant x. No, 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 no. This is like what? 1 plus 1 upon c square. So it's just 1 minus 2 upon c cube times negative sign. Just this thing. Sure. Yeah. That's what y double dash is. So y double dash is equal to, oh, and cosine square that times this thing. Cosine square y double dash. That is equal to what? Cosine square plus 2 tan of x. We know what tan of x is though, right? So y is x plus tan of x. This doesn't look like, oh, sorry, it should not be there. That one is just not there, so it's not supposed to be there as well. It's just 2 tan of x, which is like 2 and then y minus x, of course. So k is just 2. So answer is A. There we go. Okay, let's check. So first B, second B, third A, B A C, then B A D. 10th is supposed to be A. Okay. 11th D, then C, 13th A B D, 16th D B B, and 19th is supposed to be A. Okay, let's check 19th. So this is supposed to be A. Yeah, wait. Why did I? Oh, okay. I mean, we did get this result, right? 2 natural log of x minus 3 upon x cube. Why did I even choose this as well? Something went wrong. Oh yeah, I just saw x cube and then there was no x cube, I thought, and I went with it. Actually, there's this x cube over here as well, so I should have looked more closely. Okay, so that was really stupid. Huh. Even though I got the correct answer. Fine. 10th. So yes, it should be A. Okay, 10th is, so it's A. Derivative of this function is, okay, that's just wrong. That is just wrong. You cannot have something like that. It makes no sense. That natural log of 1 plus 1 upon x, where is that? That should be there, alright? It should have natural log of y and something like that, right? Yeah, this is just not correct. So 10th, their answer is just wrong. Okay, D is in fact correct. Okay, cool. And that's it. Huh. Yeah. So, okay, now you have the proper exercises. That's long, isn't it? Wow, it's gonna take a lot of time to do. Fine. So this is it. I will see you in the next video where I will do this exercise 1A. Till then, bye.